Hello. So this will be a video on perturbation theory, time independent version. I would like to say something about the mathematical background of it and take up an example to illustrate my point. The illustration and the theory is of course taken from Goldstein's classical mechanics, but the mathematical background of preliminary things I'm saying is I did not find anywhere, but I thought of my. So these are small disclaimers that so I did not find this explanation in any book. So if you find anything wrong, please let me know. An example is and content is taken from Goldstein classical mechanics, and familiarity with Hamilton-Jacobi equations are assumed. So now we assume, as in Hamilton-Jacobi formulation, we take the alphas and betas which are time independent or constants in time as the conjugate variables, and we assume here that they are real functions of time. And also in the Hamiltonian, which is analytically solvable, we add to it a perturbation Hamiltonian which is controlled by a small parameter epsilon, and when we find equations of motion on both sides, we match the order of epsilon to get our desired result. So first we assume that we know the full solutions. Say the alpha can be written as alpha 1 plus alpha 2 plus alpha 3 and so on, where each alpha I are functions of time, real functions of time, and alpha a1 satisfies perturbed Hamiltonian. We denote a1 equals to alpha superscript 0, a1 plus a2 as alpha superscript 1, a1 plus a2 plus a3 alpha superscript 2, and so on, such that this sequence of alpha superscript I is a converging sequence of functions. What do I mean by that? I will come till later. And where alpha I and alpha I plus 1 are different by order epsilon I. So what I mean is that the values they take for all time on which we are interested, they differ by the order epsilon to the power I. So alpha 0 and alpha 1 are different by order epsilon, alpha 1, alpha 2 are different by order epsilon square, and so on. Now assuming that we know the full solution, and for each step, say for example in step 1 we put alpha dot 1 equals to del h del beta at beta 1. So there actually we interchange beta 1 with beta 0 because the LHS, this is of order epsilon, and we know that beta 1 minus beta 0 is less than or equal to order epsilon, so we do not consider them that different, so we get this as evaluated at beta 0. Similarly, beta dot 1 equals to this evaluated at alpha 0. So after solving for alpha 1 and beta 1, we can actually check the order of epsilon closeness is satisfied or not. So I'm not sure, but I do not think that I'm actually interested in pointwise convergence in time, but as alpha is a solution and which is finite at all times, it motivates to think that the sequence actually follows uniform convergence for all time. That is, this set of alpha i's is such that given any real number epsilon dash, say, there exists some I such that for all j greater than or equal to I, this condition is satisfied for all time t. Yeah, it is also evident that if the sequence converges uniformly, then it converges pointwise at all times also. So in general, this is my case, alpha I dot, the nth order. When we calculate, we evaluate this thing at n minus 1th order. Same for beta I also. So now we consider an example. H naught equals to p square by 2n is the Hamiltonian of free particle, and the perturbation we are adding is m omega square x square by 2, where we take omega square as our order epsilon. Then at each order we balance number of epsilons on each side of equations of motion. So these are my equations of motion. So for h naught, p dot at t equals to 0 is 0, because p dot, h naught does not depend on x, so p dot equals to del h del x minus del h naught del x, which is 0. So p naught equals to p0, a constant, and x dot at t equals to 0 is p naught by m, which is a condition, the p given by the condition that p equals to p naught, and x naught equals to p naught t by m. Now we suppose a series solution x equals to this sum, where a1 is x superscript 0, a1 plus a2 x superscript 1, and so on. Similarly for p. Now for first order, we consider p dot first order equals to minus m omega square x 0th order. So again, this should have been x1, but x1 equals to x0 plus order epsilon, and when we multiply both sides by omega square, so this becomes order of epsilon square. But this is a equation valid for order epsilon, so we actually consider omega square x0 and omega square x1 as same, considering order epsilon. So this we get it finally. Then p dot 1 after putting x0 equals to p naught m by t, p naught by m times t, then this comes out omega square p naught t. So this gives me p1 of t as this solution. Now same we do for x dot. So x dot first order solution gives me p1 by m. So in LHS we have order epsilon, but if we use p0 here, which is not order of epsilon, so we actually can use here p1 also, and which is also we found in last step. So this is what we got, and x1 as a function of t gives me this. So these are precisely first order terms for the full solution. P of t is p naught cos omega t, and x of t is p naught by omega sin omega t. So this can also be achieved from Hamilton-Jacobi equations. So for this h naught, we write the Hamilton-Jacobi equation as this, and here the new momenta will be alpha, and the coordinate conjugate to that q is beta, which is given by del s del alpha, which is x minus alpha t by m. So x comes out to be alpha t by m plus beta, and small p, which is my old momentum, this comes out as del s by del x, which is equals to alpha. Now we can take alpha, the 0th order solution as alpha 0, and beta zeroth order solution as beta 0, which is equals to 0, and then which is just x at t equals to 0, we are taking 0. So in terms of alpha and beta, we write the perturbed Hamiltonian this as half m omega square alpha t by m plus beta whole square. So from there, alpha dot we calculating as this and beta dot we calculating as this. So like it was in previous case where we had omega square for the solution of p dot. So we could consider for first order we considered zeroth order here, and for second order we considered first order here, and so on. But there, since it was no omega square here, so we could consider the first order here, and so on. And now in this case there is a symmetry that omega square appears in both, which is of order epsilon. So again, the formulation previously proposed that for first order we use zeroth order solution, because this is also already an order of epsilon term. So for first order we evaluate this thing at alpha equals to alpha naught, at beta equals to beta naught, which is equals to 0, and this gives this, and by integrating it we get this as a first order solution for alpha. Similarly for beta dot, we calculate this at alpha equals to alpha naught and beta equals to beta naught equals to 0, which gives me this, and integrating this we get beta 1 first order as this. So now if we calculate p1, so this is just alpha 1 by this relation, so which is given by this alpha 0 minus half omega square alpha naught t, and x1, which was this, so just multiplying alpha 1 times t by n, and this gives this thing, and plus beta 1, which is calculated as omega square t square m by alpha naught. So this gives me this, so overall I get this. So this is also like first order terms in the whole solution, where x assumes a sine omega t form and p assumes a cos omega t form. Yeah, so that was it. I hope you liked it. Thanks for watching.